Hello everyone. Imagine you're outside on a clear night, staring at the sky. The stars seem steady, but the planets, those bright wanderers, appear to shift positions every night. Have you ever thought, why do they move that way? For centuries, people tried to answer this. Some said, everything moves around the Earth. That was the geocentric model. Then came Copernicus, who boldly placed the sun at the center, but still assumed circular orbits. Nice try, but not quite right. Then enters Tycho Brahe, a Danish nobleman who spent his life recording planetary positions, almost like keeping a cosmic diary. His assistant, Johannes Kepler, took those notes and, boom, he cracked the puzzle. He gave us three beautiful laws of planetary motion that changed astronomy forever. So, let's unfold these laws step by step, like chapters of a thrilling cosmic story. Kepler's first law says planets move in elliptical orbits with the sun at one focus. Now picture this: instead of a perfect round racetrack, planets follow a slightly stretched oval path, an ellipse. You can even draw it at home. Take a string, pin both ends, stretch it with a pencil, and trace. That's your ellipse. The longest line across is the major axis, half of it is the semi-major axis, A. The shortest one is the minor axis, B. The closest point to the sun is perihelion, think of it as the near hug. The farthest point is aphelion, the social distancing zone of the orbit. Look at the orbit diagram with the sun slightly off-center. So, the first lesson is, orbits aren't perfect circles. They're ellipses with the sun tucked away at one focus like a VIP seat. Now comes the second law, equal areas in equal times. Let's decode. Imagine the sun and a planet are joined by an invisible line. As the planet moves, that line sweeps out triangular slices of area. Kepler found that in equal time intervals, those areas are equal. What does this mean? Near the sun, the planet zooms faster, and far from the sun, it crawls slower. But the area covered in, say, 1 month near perihelion equals the area covered in 1 month near aphelion. Physics translation: the planet's angular momentum, that's our cross P, is conserved because gravity is a central force. So the sweep rate of area equals angular momentum divided by 2 times the mass, and it stays constant. See the shaded triangles in the diagram, narrow and long near the sun, wide and short farther away, yet equal areas. It's like skating around a rink. When you cut close to the center, you spin faster, and when you drift out, you slow down. Same energy, just spread differently. Now for the grand final, Kepler's third law. It says, the square of the orbital period is proportional to the cube of the semi-major axis. Or simply, t squared is proportional to a cubed. In other words, the bigger the orbit, the longer the year, and not just randomly longer, but in a precise mathematical ratio. Astronomers calculated this for every planet. Take Mercury, tiny orbit, zips around in 88 days. Take Neptune, huge orbit, takes 165 Earth years. And guess what? The ratio t squared divided by a cube stays nearly constant for all. See the t squared versus a cubed graph showing a perfect straight line. So Kepler gave us not just observations, but a universal pattern linking time and distance. Let's peek into the physics behind the second law. Consider a planet of mass m, position vector r, and velocity v. In a tiny time slice delta t, the swept area is half of our cross v times delta t. Divide both sides by delta t and you get area rate equals angular momentum divided by 2 times mass. Since gravity acts along r, a central force, torque is 0. Zero torque means angular momentum stays constant. So the area sweep per unit time is fixed. Diagram with R, V, and the shaded area. So what Kepler observed with geometry, physics explains with conservation of angular momentum. Neat, right? Let's put this into practice. Say a planet is at perihelion with distance r sub p and speed v sub p, and later at aphelion with distance r sub a and speed v sub a. From conservation of angular momentum, m times r sub p times v sub p equals m times r sub a times v sub a. Cancel the mass, and you get v sub p divided by v sub a equals r sub a divided by r sub p. Since aphelion distance is greater, perihelion speed is higher. Orbit diagram with speed arrows, long arrow near the Sun, shorter arrow far away. So planets basically speed up to sneak past the Sun and slow down when far away, like cars zipping by at a curve and easing up on the straight road. So, let's stitch it all together. 1. Orbits are ellipses with the Sun at a focus. 2. Equal areas in equal times, hangs to angular momentum conservation. 3. Time period squared is proportional to semi-major axis cubed, a universal timing pattern. Together, Kepler's three laws took the dance of planets from mystery to mathematics. And Newton later reveals the deeper reason: gravity pulls the strings behind this cosmic ballet. Final combined diagram, ellipse, equal area sectors, and t-squared versus a cubed plot. So next time you look up, remember, planets aren't just shining dots, they're storytellers tracing ellipses, sweeping equal areas, and keeping perfect time. That's the beauty of physics. It turns stargazing into equations, and equations back into wonder. I hope you enjoyed this journey through Kepler's laws. See you in the next session with yet another fascinating adventure in physics.